morning. Today we're going to start a discussion of our last chapter for the semester, chapter 21. In this chapter, we're going to talk about radioactivity and nuclear chemistry. Now, one thing that's going to be different about this chapter than any of the other chapters that we've talked about is that this will actually involve changes to the nucleus, right? Nothing that we've talked about in this course so far has actually involved changing the nucleus. We've discussed what the nucleus is. In Chem 1, we learned about the nucleus and all that good stuff. But chemistry, chemical reactions, right, involve the electrons, right? As we've talked about, the nucleus is just kind of along for the ride, right? We don't convert one atom into another. Well, that is specifically what we are going to talk about in this chapter, right? So, radioactivity in nuclear chemistry involve changes within the nuclei of the atom. And so we're going to explore different aspects of radioactivity and nuclear chemistry. But before we get there, of course, we should define what radioactivity is. And so radioactivity is the emission of subatomic particles or high-energy electromagnetic radiation by the nuclei of certain atoms. Right? And so certain nuclei are unstable, right? The nucleus is unstable, and we have spontaneous emission of either particles, subatomic particles of different characteristics that we'll talk about, or high-energy electromagnetic radiation. Remember, light, right? Part of that electromagnetic spectrum we talked about back in Chem 1. Now, atoms that emit this radiation are said to be what we call radioactive, right? So when we use the term radioactive, right, that means it has an active radioactive nuclei, right? So a sample of uranium-235, for example, right, is radioactive. It is giving off these subatomic particles and high magnetic radiation. And so one thing to sort of get clear right at the beginning is that exposure to radiation does not make something radioactive, right? You cannot become radioactive. You have to contain radioactive elements in order for that to happen. Now, radioactivity is used in a lot of different applications, and we'll talk about some of these a little bit more in depth at the end of the chapter. But a lot of the more important ones, at least to us, involve medicine. Right? Applications with medicine. Of course, there's some big, larger applications that we'll get into, such as nuclear energy and nuclear weapons that we'll talk about as well. But we'll talk about their use in medical conditions. Now, most of these radioactive emissions pass through most matter, right? Such as body tissue, right? Even thin metals, woods, most materials, unless they're of a certain thickness, right? Or certain types of materials will allow the radioactive emissions to pass right through them. We can also use radioactivity to estimate the age of certain things, such as fossils, rocks, ancient artifacts, right, by different methods. And this idea of radioactivity, of course, led to some other topics that I'm sure you're familiar with, like nuclear fission, used in weapons and electricity, and other things as well. So we're going to touch on some of these as we go through the chapter. Now, let's look a little bit at the history, right? So radioactivity was first discovered by Henry Becquerel, right? Now, he was looking at an experiment to look at what we call phosphorescence, right? And so phosphorescence is simply the long-lived emission of light by atoms or molecules that occurs in some materials after they absorb light. So the idea is that you put something's there, it absorbs energy, absorbs light energy, and then re-emits it over a long period of time, and we call this phosphorescence. It glows, right? This is the essence behind things like glow-in-the-dark toys, right? This is a phosphorescence. That is not radioactivity, right? We are not emitting radioactive subatomic particles, right? But does not contain radioactive nuclei, etc. So, in other words, he was looking for phosphorescence. He was studying these ideas of phosphorescence, but some of the compounds he was studying contained uranium. And so what he discovered was that when this uranium, right, even when it had not been exposed to light, if it was put in a drawer, wrapped in a cloth, and the story goes that he sort of accidentally, or maybe it was on purpose, I'm not sure we really know for sure, was near or on top of a piece of photographic film or a photographic plate. He saw that photographic plate had been exposed. So what he sort of thought about, or what he discovered, was essentially this material was emitting something that would expose the film without ever having been exposed to light over a long enough time to phosphoresce. So there was something else going on besides the phosphorescence in these uranium compounds. So they were producing rays that could penetrate matter, right, the cloth, and expose the film. Now, he ultimately called these uranic rays. And if you look here on the slide, we can see, one of his original photographic plates where the pieces of uranium expose the plate through the cloth without phosphorescence, right? Without having that, long-lived, without having that exposure to light. So Becquerel gave us the beginning, right? And so think about time frame. This is 1896, right? So the late 1800s, early 1900s. If we think about other things going on, right? If we remember back to our history, right? This is, around the same time when, people are doing a lot of work to study the elements, right? The periodic table, right, was being put together, had been put together. Thomson was doing his cathode ray experiments. Dalton would soon come up with his first atomic theory, etc. So within a 20-year period of time, there is a huge amount of information or a huge amount of research being done in the nature of the atom itself. And so all of this sort of ties together. So Becquerel has these, what he called uranic rays, because of they were coming from uranium-containing compounds. And he determined that all minerals that contained uranium produce these rays. So these were something that uranium was doing in all sorts of its forms. And they would be produced again, even though the uranium or the rocks with the uranium had not been exposed to any outside energy. Right? So this was not phosphorescence, in other words. Now, if we move on a little bit, Marie Curie comes onto the scene. So most of you, I'm sure, know who Marie Curie is. Okay? And so she was heavily into this work. Again, this is around that same time. She was working heavily in this area. And she determined that the rays were coming from, or could come from, elements besides uranium. So they were coming from specific elements, but uranium was not the only one. She also is credited with discovering 2 new elements. Radium, which is known for its green phosphorescence, along with the being radioactive, and polonium, which was named after her home country of Poland. If you look at the watch here, this is a radium watch, right? So this goes well beyond your glow-in-the-dark watch that you might, be familiar with, that has glow-in-the-dark, numbers. That is phosphorescence, right? Those glow because they're exposing them to light, and then when it's dark, you can see them. This is a radium watch, actually has nuclear or radioactive material embedded, so this will glow even after prolonged periods of darkness, right? Used for divers and aviators and people who are exposed to long periods of darkness but still need that watch to work. It emits heat as well. You'll notice that these watches tend to get hot when they're doing this. Now, it was at this point in time that these, quote, uranic rays were renamed radioactivity, right? Because they were no longer limited to uranium, that now multiple elements were known to undergo this, again, emission of subatomic particles, or high-energy electromagnetic radiation. And so what we call radioactivity is coming from Marie Curie's discoveries. And again, these nuclei are termed radioactive. Now, the next thing that I want to go into is what exactly are these particles or high-energy electromagnetic radiation? How do we describe them? What types of particles are being emitted? Well, Rutherford, who we might remember from some other very important work that he did, like nuclear model of the atom, for example, also was very big into radioactivity, right? And he's credited with discovering 3 types of decay particles, right? Of these subatomic particles that are emitted from these radioactive nuclei. The first of these is an alpha particle. So what we call alpha decay emits an alpha particle. An alpha particle is a fairly large by subatomic particles scale. It has a mass of 4 AMU and a charge of +2. So very much like a helium nucleus. So if you were to take helium, strip away the electrons, this would be an alpha particle. So as radioactive particles come, very big, the largest of these particles. Again, it's positively charged. That becomes important, right, to understand, a little bit later. And it's the size of a helium nucleus. Now, little trip down, if we were to flashback, right, when Rutherford was doing his gold foil experiment, right, you might remember that part of that experiment was using a source of alpha particles, right, that he targeted at his gold foil, right? So these 2 areas of research were coming together for Rutherford. So, his work in radioactivity, gave an understanding to what could be used to probe the nucleus that ultimately led to discovering the idea, or to probe the atom, which ultimately led to the discovery of the nucleus in the early 1900s. Now, a second type of particle is called a beta particle, right? Again, symbolized by the Greek letter beta. So we say this so-called comes from beta decay. Now, beta particles are much, much smaller. They are about the size of an electron. They have a -1 charge. And again, very little mass. So very much electron-like. But, of course, emanating from the nucleus, not around the nucleus. And then, finally, the last one he discovered was not a particle, but a form of electromagnetic radiation. And these are what we call gamma rays. So if you remember back to our study of the electromagnetic spectrum, the highest energy area of that spectrum that we look at are called gamma rays, again abbreviated by the Greek letter gamma. And this, again, is a very high energy form of electromagnetic radiation. Not a particle, has no mass. Now, so those were discovered by Rutherford. Now, there are some other types of radioactive decay that we can characterize as well. These are what we call positron emission, which is like a beta particle, but positively charged. So sometimes we characterize it as a positively charged electron. So some nuclei will emit a positive or electron or a positive beta particle or positron. Other nuclei will do what we call electron capture as a form of radioactive process, where they don't actually lose a particle, but they actually absorb a particle. So electron capture is just what it says. The nuclei will absorb an electron from outside of it, right? So we think about those electrons outside the nucleus. Some of those are very close to the nucleus, and that electron capture is absorbing an electron into the nucleus. So these are sort of 5 processes of radioactive decay. Alpha decay, emission of an alpha particle. Beta decay, emission of a beta particle. Gamma, emission of a gamma rays. Positron emission, emission of a positron. And electron capture, which is absorption of an electron into the nucleus. So, we can talk about these radioactive nuclei, right? And that's sort of how we refer to them. We talk about nuclides, right, is the typical nomenclature that we talk about. So we have individual nuclides, because now we don't really care about the rest of the atom. We care about the nucleus, so we just focus on the nucleus. If we remember, a nucleus is characterized by a couple of numbers, right? We have the atomic number, or Z, right, which represents the number of protons contained within that nucleus. And an atom will have, remember, different versions of that, versions of its nuclei, what we call isotopes. So isotope notation or isotopes are going to become very important again when we start talking about nuclear chemistry. And, of course, the way that we identify that isotope is by using the other characteristic number of the nucleus, which is the mass number, right? Abbreviated by the capital A there, which is simply the number of nuclear particles, right? The number of protons plus the number of neutrons. So, by using the atomic number and the mass number, we can characterize these isotopes, and we can characterize these specific, what we call nuclides, right? Or nucleuses. Now, we have ways to symbolize this, and this is a review, right? We've seen this before, but typically we will write out the chemical symbol for that element, and on the left-hand side, the superscript will represent the mass number, and the subscript will represent the atomic number of that specific nuclide. Now, there are various atomic symbols that we need to become familiar with beyond the alpha and the beta and the positron. So we have protons, right? So sometimes we'll look at protons like this, like a P with a positive charge, but you will also see protons symbolized by a nuclear symbol, that will either be the letter P with a 1, 1, right? So what this is telling me here is the top number is indicating the positive charge, right? Or the mass number, right? That we have a mass of 1 proton, and the bottom number there is the atomic number, right? That it has 1 proton, that it represents 1 proton. So it's symbolized by a 1, 1, right? Often represented by a hydrogen nucleus, right? So a proton is essentially a hydrogen nucleus. We have a neutron, right? So remember, neutron we can symbolize like this, representing no charge, right? We also represent a neutron like this, where the top number, the mass number, right, a 1, right? Same mass as a proton, but it has a bottom number, an atomic number of 0, right? There are no protons, right? Or in other words, no charge, the bottom number. We have electrons, E minus, right? It's the typical symbol. Its nuclear symbolism is often a top number of 0, representing the fact that it has essentially 0 mass compared to the proton and neutron. And the bottom number, again, its charge, a -1 indication there. An alpha particle, right? It's either abbreviated as an alpha 42, right, with a mass number of 4, right? 2 protons, 2 neutrons, and atomic number of 2, representing the 2 protons. Again, this is often represented as a helium nucleus. Beta particles, beta or beta minus, right? Again, can be abbreviated either as a beta with a 0 and -1, right? Very small mass, -1 charge, or again, we often represent it simply as an electron. Positron is essentially a positive beta particle, is the symbolism we use. So the same as a beta particle, but a +1 on the bottom, and or sometimes listed as a positive electron, right? A positron. So we want to get used to that symbolism when we write out nuclear equations, right, which we'll be doing. So now I want to talk a little bit more specifically about the types of nuclear decay, and more importantly, how do we represent those decays, right? How do we track or look at what nuclei will be formed if we start with a certain nuclide undergoing a certain type of decay? And the way that we outline this is something called nuclear equations, right? So these are kind of like chemical equations, but describing radioactive processes, right? So that'll look sort of like a chemical equation, but we're keeping track of different ideas here. So these are called nuclear equations. And the two things that we really want to focus on here are, if we look at both sides of the nuclear equation, the top numbers must balance out, right? So if we think about the mass numbers on top have to balance out. So you can see here we have 238 mass number here. We have 234 and 4, 238 mass number. And the bottom numbers, right? The atomic numbers must also add up. So 92 here, 90 and 2 here. So we must have a balanced nuclear equation, meaning the top numbers have to balance and the bottom numbers have to balance on both sides of the equation. So that's how we balance a nuclear equation. Now, the language that we use, right? So the reactant, if you will, or the starting nuclide is called the parent nuclide, and the nucleus that we form is called a daughter nuclide, along with whatever type of radioactive particle might be formed. So now what we're going to do is we're going to take this basic idea of a nuclear equation and look at how we would outline a nuclear equation for each of the types of nuclear decay. So we'll first look at alpha decay. So alpha decay occurs when an unstable nucleus emits one of these large alpha particles composed of 2 protons and 2 neutrons. Now, typically, alpha decay occurs in very large nuclei, right? Because alpha decay is the most efficient way to lose mass from the nucleus, right? Because we're losing a mass of 4. And so we'll see alpha decay in typically very large nuclei. It is, in terms of characteristics, so we're going to go into and characterize these different types of decay, right? It is the most ionizing, but the least penetrating of the nuclear processes, right? Or the nuclear particles. Now, what do we mean by these? Well, first of all, ionizing, right, is the ability to ionize other molecules. So, create ions, in other words. So, one of the ways that radioactive nuclei do their damage, right, if we think about how they might damage human tissue, is they ionize molecules in the body, right? They create ions where there shouldn't be ions, and those particles now are ionized. Sometimes we might call them radicals, right? And they damage. They don't function properly, etc., right? So ionizing is damaging, creating ions, turning normal healthy molecules into ions when they can't, so they can't function the way they normally would. So alpha particles are very dangerous because they have a strong ability to ionize molecules, but they're not very penetrating, right? They can't really penetrate into the body, right? They can't pass through skin. They have a very low penetrating ability. So the easiest way, to protect against alpha radiation is just, surface protection, right? They can't pass through clothes. They can't enter the body from external sources. Now, in terms of defining an alpha particle, in terms of the decay process, we look at starting with our parent nuclides, such as uranium-238. We get expulsion of an alpha particle, right? Something that might look like this, from that nucleus, and we end up with a nucleus that now has 2 less protons and 2 less neutrons. So the mass of the nucleus has now gone down by a total of 4 AMUs, and the atomic number, or the number of protons, has gone down by 2. So we know this is going to turn into something that has an atomic number. If we started at 92, we know the atomic number is going to drop down to 90. So we could identify that as a thorium atom, right? So a lot of the ways we identify this are looking at the changes to the atomic number. And that particular thorium isotope, or this thorium nuclide, would have a mass number of 234. Of course, we show the alpha particle or helium nucleus as the other product here. So that's alpha decay. Beta decay. This is when an unstable nuclei emits structurally an electron, right? We call it a beta particle, but functionally it's emitting an electron. Now, beta particles, of course, are much, much smaller than an alpha particle. They are much more penetrating, right? So 10 times more penetrating than alpha particles. So these can penetrate through clothing, penetrate into the body from external sources. But they're only about half as ionizing. So while they can penetrate, they don't do as much damage in terms of their ionizing ability. But they can pass through things like thin sheets of metal, etc. Again, if we track this, what we see is if we start with our parent, like a radium-228 isotope, we know that the atomic number, right, is going to go up by 1, right? Because if we look at a beta decay, right? It has a 0, -1 notation, right? So it causes the mass number to remain unchanged, right? So we're not eliminating a nuclear particle. We're eliminating essentially a very small mass particle with a negative charge. So we're eliminating a negative charge from the nucleus, if you will. And so that causes the number of protons to actually change by 1, right? So we gain a proton during a beta decay. So I think a really good way to think about a beta decay is not only loss of a beta particle, but structurally in the nucleus what happens is that one of the neutrons turns into a proton, right? So if you think about a neutron, right, has a mass of 1 and no charge. So if we take that neutron and we take away a negative charge, well then all of a sudden that neutral particle is now positive, right? We've thrown off the balance. So we've taken a particle with the same essential mass, but changed it into a positively charged particle or a proton. So the functional result of a beta decay is turning a neutron into a proton. And we'll see later this can be beneficial to stabilizing an unstable nucleus by changing the ratio between protons and neutrons in the nucleus. So mass number doesn't change, atomic number actually goes up by 1. We add a proton. So we know radium is going to become actinium here. Now, gamma emission. Now, of course, gamma emission doesn't involve any change in the nucleus itself, right? Because it's just an energy change, right? We're emitting high energy photons of light. So we don't have any change to the atomic number or mass number directly. Now, gamma is the least ionizing, right? So it has, in essence, the least of all of the particles' ability to do damage, to ionize. Now, that doesn't mean it's harmless, of course, in terms of ionizing, but it is by far the most penetrating, right? Can penetrate several inches of lead, you know, something we typically think about shielding from radiation, or concrete, right? So by far the most penetrating of the 3 basic types of nuclear decay. Now, that being said, gamma typically occurs alongside some other particle decay, right? Such as alpha or beta decay. So if we look, for example, at, again, that decay of uranium-238, we saw earlier that it generated a thorium-234 process, an alpha particle, and it also emits gamma rays. Now, again, gamma rays don't functionally change any of this, but we can note them as an energy product, right? So where we tend to see gamma radiation is accompanying other types of particle decay. Now, of course, not always, right? It can occur by itself, but just this is where we tend to think about it. So, just to kind of review these penetrating abilities, if we think about alpha, right, gets stopped by a very, very thin sheet of lead, right? But again, has the highest ability to ionize particles. Beta particles can pass through thin sheets of lead, but will get stopped by a little bit thicker. Now, none of these are very thick, right? Even this medium one is a millimeter, right? So it takes about a millimeter thick sheet of lead to stop a beta particle. And again, it has sort of a medium ionizing ability, right? Gamma rays can penetrate even fairly thick sheets of lead up to 100 millimeters, right? Or 10 centimeters thick of lead. But again, are the lowest ability to ionize of the three. So now we can look at the other two types of nuclear processes, positron emission and electron capture. So positron is the opposite of beta. So we have a change of +1 and a negligible mass change. So what we see is where we saw beta decay, we saw an increase in the atomic number. All right, we saw a neutron functionally changing into a proton. Now what we see in a positron emission is a proton in the nucleus functionally become a neutron. So we take this positively charged particle, it loses a positive charge in the form of a positron or a positively charged electron. So the mass basically remains unchanged, but now that positive has become neutral or functionally a neutron. So this does the opposite of a beta decay. So what we see here is we see nucleuses that, again, need to change that ratio of protons to neutrons, and they're likely to undergo positron emission if they need more neutrons and less protons. Whereas a nucleus that needs more protons and less neutrons is likely to undergo beta decay. So similar ionizing and penetrating to a beta particle. So very similar in most ways to beta, except for what's functionally happening in the nucleus. But again, notice the balance top to bottom and the functional result of the atomic number going down 1. So phosphorus is going to turn into silicon. Lastly, electron capture. So this occurs when one of those very inner, lower energy level, 1s if you will, right, electrons gets pulled into the nucleus. Again, no emission, but the nucleus changes. So this is the one time where we see an actual change in the nucleus without anything actually being emitted from the nucleus. Now notice in the nuclear equation that it's shown on the reactant side, right? There is nothing on the product side besides the daughter nuclide. So what we see is, again, no change in the mass number, but a decrease in the atomic number. So we go from, in this case, ruthenium with a 44 to technetium with a 43. So functionally, again, what's happening here is that a proton is becoming a neutron. So what we're seeing is the same ultimate change as what we saw in positron emission, but a different mechanism. So some atoms will undergo positron emission, other atoms will undergo electron capture. But ultimately, the same net effect here. Now finally, we can sort of just point your attention to this chart in the book where it's a really good summary of these 5 different modes of radioactive decay: alpha, beta, gamma, and positron, and electron capture. And of course, you should be able to characterize these, describe them. You should be able to work with or balance chemical equations, or nuclear equations that involve these. That involves things like predicting the products. If I tell you the type of decay, writing them out. If I gave you the parent and the daughter, you could tell me what kind of decay that was by understanding the balancing, that the top numbers have to add up, the bottom numbers have to add up. We want to know the characteristics of these different types, right? Their penetrating ability, their ionizing ability. So we want to be able to put all that stuff together. One of the things we're going to look at in the next section is this N to Z ratio, right? And the effects of these different processes on that crucial, what becomes a crucial ratio for predicting stability of a nucleus, right? And again, this N to Z ratio is the neutron to proton, right? Z coming from the atomic number, which is the number of protons, right? So this is the neutron to proton ratio in a nucleus. And so we'll get into predicting stability based on that in the next section here. To close out this section, I just want to do a couple examples for writing nuclear equations for these different decay processes. So I have three here that we want to talk about. So we're going to look at the alpha decay of polonium-216, the positron emission of sodium-22, and the electron capture of krypton-76. We're going to write out these equations. So, of course, the first step is to start with what we're beginning with, our parent nuclide. So, of course, remember this type of notation, right? This is another form of isotopic notation where they give us the symbol or the name followed by the mass number, right? So this is going to be the top number in our symbolism. And then, of course, from the periodic table, we can figure out the atomic number here. So we're going to start with our parent nuclide. And we say that we're undergoing alpha decay. So our parent nuclide is going to undergo. Now, I'm going to be sort of the same way that they do it in the book, where they put the daughter nuclide first and then the atomic particle. So I'm going to write over here our alpha decay, right? So this would either be an alpha 4-2 or a helium 4-2. And so now the key becomes predicting what this is going to be, right? So what I like to do is do both the top and the bottom. So the bottom is, the first key, because I know that both sides have to equal 84. So what I essentially know is that the atomic numbers is going to be 84 equals x plus 2, right? So what that tells me is that x equals 82, right? So I need a nucleus that has an atomic number of 82. So if I look at my periodic table, that tells me that that is lead. It's the element with an atomic number of 82. And of course, this particular isotope of lead will have to have a mass number that where we have 216 equals x plus 4, or x equals 212. So tops add up, bottoms add up. That's my balanced nuclear equation. So that's the basic idea. So let's look at another one. So again, we have, in this case, positron emission. So we have an emission of the particle. So the particle is going to go on the product side. So I'll leave my space there for my daughter. And remember, a positron is simply an electron with a positive one on the bottom and a sorry, let me rewrite that a little more clearly for you. With a positive one on the bottom. Okay. So I know, again, my atomic number. So my Z here, I just did this. So it's 11 on one side equals x plus -1. So if I add, excuse me, gosh, gotta write it right here, sorry. X plus 1. And so X has to equal 10. So I need something that has an atomic number of 10. So if I convert my periodic table, that's going to tell me that my nucleus here is neon. So 10 and 1 gives me the 11. And this particular isotope of neon would also have a mass number 22 because the mass number doesn't change in positron emission. So my sodium has decayed into a neon by positron emission. So we've lost a proton, but maintained a mass number, so that means that proton turned into a neutron. Now, electron capture of krypton 76. So the key here is the electron capture. So remember, the difference here is that my decay particle, or my particle that I'm going to be looking at, is going to be a reactant because I'm capturing it. And again, I'm capturing an electron, so which will look like that, and then I can figure out what my daughter nuclide is. So I know my daughter is going to have a mass number of 76, and the key is, what is the atomic number? Well, 36 plus a negative 1, so 35. So I need to find the element that has an atomic number of 35. That's going to be bromine. So my daughter nuclide is bromine 76, or bromine with a mass number of 76. So again, just like positron emission, I have a net reduction of 1 in the number of protons, an increase in the number of neutrons. Okay, so that's writing nuclear equations, and there's different ways that you can do it in terms of, you should be able to do this for all the different processes. You should be able to do other examples where maybe they give you both the daughter and the parent and you predict the type of decay, these kinds of things. So in our next section, next video, we'll talk about nuclear stability and how those nucleuses behave.